So what are we doing? And now this is where my little band of revolutionaries come in. And this is, again, Dr. Kogi's thesis here, his formulation. If memory bandwidth is the issue, one thing that you can do is put the processing near the memory. Have you guys studied processor and memory architectures yet? Okay, so you've even done that. Excellent. So this is something that Dr. Kogi was very involved with for years now. He's been thinking about how you do this. The idea is you take a little bit of processing, and what we call it is a memory side processor, and you put it close to the memory and you let it do sort of small things that may help you when you get to the big cores, little atomic operations or memory accesses or additions or multiplications, simple small things that you can do that will reduce the burden on the cores, reduce the bandwidth requirements, and make the algorithm run more efficiently. So we call that memory side processing. And the analogy would be, if I go back to my peach orchard, if I have to pick a special kind of peach, I don't bring them all into the kitchen and then throw away the ones I don't want. I go to the tree and I only pick the ones that I want. I move the processing into the memory. Second thing that I can do, if scaling, I talked about scalability in the parallel processor, if that's the issue, instead of doing this data access thing to a remote memory that I talked about, I can actually move the processing. So we have this thing in our architecture called migrating threads, where if a thread is a unit of processing, it's like a unit of work that the core does. I actually take that thing, and instead of accessing a remote memory over the network, I move it, and I just continue my processing over there. Now, this is a pretty radical concept. There is pretty much no computer out there that does that to the extent that we're doing it. We're doing this in the hardware at a very low system level. People have talked about doing this. Some people have done it at the operating system or at the system level. There's nobody doing this in the hardware, and that's what we're doing. So the idea is you're going to reduce the bandwidth requirements, but because you don't need access data, you just migrate a very small context over to the other core. And I've got some animation that talks about that. So here's a conventional design. There's my program, which is relatively small compared to the data, because this is the big data world. And I've got like 4 distributed memories, and I've got this program. And let's say I need to access all of them. Well, here's what I'm doing. I'm doing 8 fetches and stores to memory over the network. And remember, each one of those fetches is hurting my efficiency and hurting my performance. So you have a lot of data that's moved through a very limited network. So what is it that we're doing? We are doing this. Program accesses memory. Then it wants to access the next memory. But instead of accessing that memory, you move a context. And then the next one, you move a context again. You move a context, and then finally you can come back if you need to. So we have half the number of network transactions that a conventional computer has for the same kind of thing. And that's basically the idea. What you're doing is you're not moving a whole program, because a program is decent size. You wouldn't move the whole program. The idea is that the program lives in the memory of every core, close by the core. What you're actually sending around is a program context, a program counter. You guys study that stuff. A state, a thread state, which is small, maybe a couple of registers, a small state. So what are we doing with this? So we don't have the bottlenecks that we're going to have in other architectures, because we've got this memory side processor to reduce that. We've got fine-grained parallelism. We can have lots and lots of these really small cores. All of this is very efficient because it's done in hardware. It's invisible to the programmer. Basically what happens is when the system sees that a memory access is made to a non-local memory, the hardware ships up the thread state and ships it along. So the programmer never even needs to worry about it. So it's ideal for these big data applications that don't have the locality, but they also have these real-time requirements. So that's the idea. And here's what we have. Here's what we're building. This, we call it the chick here, is our small system. This is what we're delivering today. That has 8 nodes in it. Each node has 8 what we call nodelets. Each nodelet has 4 cores. Each core is capable of running 64 threads. I have this all in a picture. In the interest of time, I didn't put it up. But anyway, the point is lots and lots of threads can live in this system. And then so what's shown in the picture there is a node board. When we go to our large servers, which we're going to be shipping at the end of this year, it's the same node board, but lots and lots of them in sort of a server room looking refrigerator cabinet. Same architecture, same system. That's going to be liquid cooled, so you're going to have lots and lots. So we're going to scale that thing up to 250,000 of concurrent threads, which is really big. There aren't any systems that do that today. So this is what we've got. And to finally leave you with, what is it going to be good for? We're just starting this stuff. This is just the tip of the iceberg. We've just started the revolution. This is where we think it'll work, and we've started looking at these areas. We've got some benchmarks that relate to these areas. But these are all up-and-coming things. Cybersecurity, malware detection, right? That's huge. Unsupervised learning in the AI world. We think it'll play nicely there. Non-obvious relationship analysis, processing your social networks or looking for relationships in documents, etc. Weather forecasting, oil and gas, fluid dynamics. Again, some of these are, we think they'll be great because they're graph-like. Some of them we think they'll be great because they're sparse. Somewhere in there is a really sweet spot for us. And as I mentioned, we've just started. So I think that's it. And I think I fit that in 20 minutes. So I hope I hit the right level. All right, thank you.